Hello everyone. In this session, I'm going to discuss about the quantum gates for multiple qubits. It's is for your exam point of view, as I'm not given the all the quantum gates which are useful for the multiple qubits. Exam point of view, there is enough enough to write about the two gates. So here I mentioned the CNOT gate. One is like CNOT gate. Second one is like CZ gate. I have written like a two gates. One is CNOT. Second one CZ. So in what way we can write exam if he is asking about the write or explain the different quantum gates for multiple qubits. So obviously we need to understand why the quantum gate is suitable. So the quantum gates are suitable for the operations related to the quantum states. It changes the state from one state to the another state of particular quantum system. Here, the multiple qubits. Obviously, we should understand in case of the quantum computing point of view, the information is stored in the form of like a qubits. It is similar to the classical bits like a 0, 1. But in case of the qubit point of view, the advantage of the qubit is superposition. That is, the information can be stored simultaneously in both the state, which is not possible in case of classical bit. So that is represented by using the superposition like psi equivalents to alpha state 0 plus beta state 1. This the superposition related to the single qubit where alpha beta are the amplitudes and alpha square and beta square is called as probabilities. For to represent the single qubit, we already discussed relate to the X gate, Y gate, Z gate. These are the Pauli's gate. Hadamard gate is related to the formation of superposition principle by using the input gates. This part already we discussed. And coming to the here it is given for the multiple qubit point of view, right? So for what purpose we need to study about the multiple qubits? Obviously, the multiple qubits speciality is it creates the entanglement. This is one of the most important concept related to the entanglement and quantum algorithm. Quantum communication means how we can communicate the data from one place to the another place and how we can correct the information like error correction. So this part we need to understand. So here the multiple qubit advantage is it is suitable for the entanglement. It is suitable for the quantum algorithm. It is suitable for the quantum communication, and it is one of the supporting for error correction. Then, but exam point of view, what we need to write is asking about the information about the quantum gates for multiple qubits. First, I start with the start with the introduction related to the quantum gates, and then I just discussed what are the gates available for the one qubit, like a single qubit, and what is the meaning of the qubit. That part I discussed initially, and then I just start with the what happen if it is more than two qubits are available in that particular system. For example, one qubit, we have states like 0 state. As we know, the state is represented with the ket 0 and ket 1. This also we already discussed. The ket advantage is it is the representation of the states. But how many states? 0 state and 1 state. We have two states here. So one qubit, we have the two states like a 2 power 1. Similarly, we have the 2 qubit. If we have the 2 qubit, we have two square states. That part is like 0, 0, 0, 1, 1, 0, 1, 1 states. So we have for the 2 qubit point of view, we have 4 states. But how we can represent these four states like a superposition? Here, as you see here. This is the general state relate to the state superposition for the two qubits. That is alpha, beta, gamma, delta are the probability amplitudes, and alpha square plus beta square plus gamma square plus delta square, which is equivalent to 1. We have finally, we have four states related to the two qubit system. But what about the three qubit system? We have 2 power 3, total 8 states. We have 8 states. That part I am discussing here. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Similarly, 8 states we are having. So how we can write these states like a superposition? Obviously, we need to write it as like same previous case. Alpha 1 state 0, 0, 0 plus alpha 2 state 0, 0, 1, alpha 3 state 0, 1, 0, etc. All the probability amplitude must be equivalent to the square of the probability amplitude must be equal to 1. That is the normalization concept, and number of states is here. Till here, I just discussed about the introduction related to the what is the meaning of the multiple qubit and what is the advantage of using multiple qubits. That part I discussed a little bit because we are writing for the quantum gates for the multiple qubit system. Without giving the information related to the multiple qubit, there is no meaning to write the direct quantum gates. That's what I just given the small introduction related to that. Now, coming to the controlled NOT gate, it is one of the important gate, especially for the 2-qubit system. This is like controlled NOT gate, like CNOT gate. Here the thing is, in case of 2-bit, we just discussed about the 0, 0 state, 0, 1 state, 1, 0 state, and 1, 1 state. For example, in these two states, one is related to the first qubit, another is related to the second qubit. First, you try to understand the first value is related to the controlled bit qubit. The first value is related to the controlled qubit, and second value is related to the here. For example, this is the second one, 0. Another 0 is related to the target qubit. We are not changing the controlled qubit. There is a change we observe in the target qubit when the controlled qubit is equivalent to 1. That if such kind of data is or such kind of changes is needed, we are using the controlled NOT gate. In case of controlled NOT gate, if the controlled target or the controlled qubit value is equivalent to 1, then target is flips. If the target is flip. For example, just we discussed, we have 4 states, right? We just discussed the 4 states. For example, I just take it as like a 0, 0 state. Now I am applying the CNOT gate. Here the CNOT gate representation of the gate is like A, B of this the representation related to the A comma. This is the representation related to the CNOT gate. For example, in this particular situation, A is the controlled and controlled gate, and we are applying the CNOT. If the controlled gate is 1, then CNOT gate is applied, that is flip is possible. For example, here it is 0, 0 state. Control gate value is 0. I just mentioned control gate is 0 and target gate is 0. Whatever our requirement, control gate is not 1, right? Then the final result value state is related to the 0, 0. For example, in this particular state, Here again, control gate value is state is 0 and target value is 1. But if the control, as per the word related to the CNOT gate, if the control gate is 1, then only the target gate is flips. Here that is control gate is 0, right? There is no change in the target gate. Then final answer is 0, 1. Similarly, in case of 1, 0, see here, the control gate is 1 and target gate is 0. But what we mentioned, if the controlled gate is 1, then the target gate is flips. So here it is 0, then it changes to the 1, 1. Similarly here, controlled gate is 1, target gate is 1, but target gate flips, right? Then the final state is, if it is 1, 0 state, it become like 1, 1 state. If it is 1, 1, it become like 1, 0 state. So the based on this particular information, we are applying the truth table. See the truth table. What I mentioned, if the control is 0, target is 0, there is no change in the target because there is already control gate is 0. If the control is 0, target is 1, 0, 1 state. If the control is 1, just see here, the control is 1, the target is 0, then it make it as like a 1, 1. Then again the control is 1, but the target is 1, target flips, right? That's what 1, 0. So this is the thing related to the CNOT gate. This is a structure related to the C gate. It is the input first coordinate, like a first state, and this is a second state. The representation of the control gate is X, this is a symbol, and Y. Operating on a 2-qubit system, the CNOT gate is represented by the 4 by 4 unitary matrix. So, and it is unitary matrix is operated based on the base states like 0, 0, 0, 1, 1, 0, 1, 1. Till now, I just discussed about the things, what is the concept. Now, if you want to check in a matrix form, first we need to take the matrix representation of the CNOT gate. See here, the matrix gate 1, 1. Here it is not 1. This is the 1. Then these values are changed. Unitary matrix is these two rows are interchanged. This is the CNOT gate matrix form, like a 2 by 2 matrix. If the CNOT gate operates on the 1, 0 state, as we previously discussed, how we can write the matrix of the 1, 0 state. This is the tensor product, state 1. Need to take the tensor product with the 0. We already take it as like a 0, 1 here. And tensor product with the 1, 0 state. So this is the matrix representation. So when we are applying like this is the 0, 0, 1, 0. The same matrix we are applying here. That is, this is the CNOT gate fundamental matrix. And it is operate on the 1, 0 state, 0, 0, 1, 0. When you are applying the matrix multiplication formula, then we are getting like a 0, 0, 0, 1. This relate to the 1, 1 matrix. So that means that this is the control gate and this is the target gate. If the control gate is 1, target gate flips. Here the target gate is 0, then it make it as like a 1. This is the representation in terms of matrix form. So this is very easy to represent the matrix form and to check the different kind of states by using the matrix form. And coming to the truth table relate to the KIT form, just we mentioned like when we are changing like a C is 1, first control bit is 1, then only the target flips. If the target is 0, it make it as 1. If the target is 1, it make it as 0. This is the advantage related to the CNOT gate. Similarly, we have one more gate, is one of the easiest gate, CZ gate, that is called as controlled Z gate. So here the advantage of the controlled Z gate are where we are using the controlled Z gate. Whenever you are requiring only the phase change of particular state without changing the other states related to the 2-qubit system. As I mentioned, like we have 4 qubits, 4 states for the 2-qubit, like a 0, 0, 0, 1, 1, 0, 1, 1. See here, this is not changing. This is not changing by applying the CZ gate. This is not changing, but this value, when you are applying the CZ gate of 1 1 state, it make it as like a minus 1 1 state. Whenever we require only the flip of 1 1 state without altering the any other thing, then we are using the CZ gate. So see here. Just I mentioned the same. Unlike the CNOT gate, the CZ gate doesn't change the bit values or 0 or 1. Instead, it only changes the phase of the quantum state. 1 1 state is changes to the minus 1 1. This is a symbolic representation. The both are look like same. That is controlled qubit and target qubit. Both are just symbolically represented as Z. So this is the truth table related to the GET form. Matrix point of view, see here it's a unitary matrix, except here the number last digit is minus 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 minus 1. This is one of the most important parameter to represent the CZ gate in the matrix form. Whereas in case of CNOT, these two lines are interchanged without minus. So what happened if the controlled Z gate is operate on the 1 1 state? What we mentioned as per the discussion, it should be like minus 1 1. So the same thing we are checking with the matrices. See here. So this is the just mentioned like a CZ gate matrix. It is operate on the 1 1 state. Then obviously it is getting the same value with minus sign, which is nothing but minus of 1 1 state. For example, if someone asks, what will happen if the CZ gate operates on a superposition state? First, we need to take the superposition state. We need to take the superposition state. That is nothing but alpha 0 0, beta 0 1, or gamma 1 0, or delta 1 1. So what about what happened if this superposition relate to the particular quantum bit state, if the quantum state by using like a CZ gate. Once CZ gate is operate, CZ only changes the 1 1 with only the flip change, like a phase change without changing the state. So here in the plus delta is changes to the minus delta because 1 1 state is become like a minus 1 1 state. That is enough. So in case of the CNOT gate, just only you should understand. In case of the CNOT gate, what will happen? In case of CNOT, only in the out of controlled gate is one value, then target flip. That become like 0 become like 1 or 1 become like 0. Whereas in case of CZ, only 1 1 state, if it is operated by the CZ, then it become like minus 1 1. That's enough relate to the quantum gates for multiple qubit system, especially for the exam point of view. Just write these two states. If need, I will provide the other details related to the swap gate or bell gate, etc. Right. Thank you.